Hey, welcome back. We are looking at solutions again today. We're going to continue our discussion about solutions, and we are going to look at a measurement called molarity. Remember in a previous video we were talking about saturation, and we were talking about measuring something called solubility, which is how much can you dissolve, what's the maximum amount that you can dissolve in 100 grams of the solvent, often water, at a specific temperature. So solubility was a measurement for the maximum amount that you can dissolve. But it'd be nice too if we had a value that measures the concentration of any solution even up until the point where it is saturated. What about when it's not saturated? How much do we have dissolved in that water? How much salt? How much sugar? So this measurement today, we're looking at a measurement, and it is called molarity, where we're going to measure how much is dissolved in a particular solvent, how much solute is dissolved in the solvent. It doesn't have to be saturated. Okay? Solubility, the previous video, was simply for when it is saturated. What's the maximum? But now we're going to talk about at any point we'd like to measure how concentrated is the solution. And this is what molarity does for us. So basically we're going to be looking at how can the concentration of a solution be expressed quantitatively. Let's get an actual number instead of just saying it's strong, it's weak, it has a lot of color, it looks very light. We want something that has an actual value to it. Okay? And this is what molarity does for us. So basically we're going to be looking at the ratio of the solute particles to the volume of the solution. It is going to be a ratio again. It's going to be a certain amount of solute per volume of the solution. Okay? Remember we talked in previous chapters or previous videos that often when we're talking about the number of something in chemistry, we're looking at moles. So moles of solute, and here we're told it's going to be volume of solution. And often in chemistry we use liters for the solution. Okay? So that's what molarity is, capital M. It is the moles of the solute divided by the liters of the entire solution. Okay? Let's dive into model 1 here. It gives us different lemonade mixtures, and we are told here that both pitchers were filled with enough water, the solvent, to provide 2 liters of solution. Okay? And then it says here, lemonade solution number 1, we obviously added whatever the mix is to make your lemonade, and lemonade number 2, we added some of the mix as well. And you can see just from the colors that this one looks a little bit weaker. It's not as concentrated. This one over here is a little darker, it's a little more concentrated. But again, we don't just want a quantitative value. We don't want just a descriptive value. We want an actual qualitative value. We want a number that we can attach to this. The particles here are going to represent the solute, how much is dissolved. So you can even see from the diagram, less is dissolved in solution 1 than in solution number 2. Alright, what is the solvent in this scenario? In this scenario, the solvent is going to be our water. Okay? The solute is going to be the lemonade mix. And what is a dissolved lemonade mix particle represented by? That is the dot that we see right there. Circle the word that best completes each sentence below and justify your answer based on the diagram. So, lemonade solution number 1 has more, less, or the same volume of solution number 2. Well, volume-wise, we are told that both pitchers were filled with enough water to provide 2 liters of solution. Okay? So these have the same volume, same exact volume for both of them. Lemonade solution number 1 has more, less, or the same quantity of solute as solution number 2. Describe how you know in terms of number of particles. Well, the number of particles is describing here for us that you have fewer than we have over here in the same sample. Imagine this is a sample that's being taken, you only have 3, whereas over here we've got 9. It's 3 times the amount over there. Okay? So solution number 1 has less particles, less solute. Solution 2 is considered to be concentrated, and lemonade solution number 1 is considered to be dilute. Examine the 2 pictures. List 2 ways to differentiate a concentrated solution from a dilute solution. Well, you can look at color. Okay, if you just look at color, that means that you're going to see the darker one is going to let less light through because it is more concentrated. It has more particles in there that are blocking the light from passing through. So you could look at color if you want to. The other way is you could taste. So if you want to taste it, the concentrated one, if this is sugar, for example, is going to taste sweeter. You're going to actually taste the difference between the two. Okay? If you're looking at their pictures, examine the 2 pictures here, obviously more particles means more concentrated. Okay? So the higher the concentration, the more particles, the more solute particles it has to have dissolved in the solution. A glass is filled with the concentrated lemonade solution from Model 1. Is the solution in the glass the same concentration as the solution in the pitcher? Yes, it is. It doesn't matter how much. It doesn't matter if you were to pour 5 glasses. They would all taste the same. If this was thoroughly mixed, they would all taste the same as far as the concentration of the mix that is in this particular lemonade solution. Okay? So the measurement of molarity is not going to be dependent upon the volume that you're pulling from your sample. This sample has a specific molarity. And it doesn't matter if you pour a big glass or a small glass, the molarity is going to be the same. The concentration is the same. Okay? Does the solution in the glass contain the same number of solute particles as the solution in the picture? Well, no, it doesn't have the same number of particles, but it has the same ratio of particles to volume of solution. Okay? Yes, of course, this little glass here has fewer particles in it of solute than the big pitcher, but the ratio is the same, meaning number of particles to its volume is going to be the same as the ratio over here of number of particles in the pitcher to its volume. The ratio is what is going to not change. Do the terms concentrated and dilute provide any specific information about the quantities? No, and that's my point here, is that it would be nice if we had something that was a value that we could attach to them. So if we just say concentrated, that's maybe somebody's opinion. They drink the lemonade and say, "Oh, this is really strong." Somebody else drinks it and says, "No, I love it like this. This is exactly how I like it. It's not strong at all. It's not concentrated." So it is not as specific as we'd like to get in the scientific world, because we would like to have an actual value attached to these numbers so that we can compare. We would like to compare different solutions, and then we'd actually look at the numbers and say, this one is definitely more concentrated than the other one. Okay? Alright, model number 2, we have dilute and concentrated, we are told, and we have number 1 and number 3, and then down here we've got number 2 and number 4. And you'll notice that what we're given here is we're given these chemical solutions, and we are given some data. We're actually given some numbers this time. So we are told that we have a certain number of particles in a certain volume. Here, look at the measurement. See the measuring here for us, the solution? Here we have a certain number of particles. Here we have a certain number of particles. And here we have a certain number of particles in this volume. Okay? In 1 and 3, we have The same solid that's being dissolved, the same solute. This is copper 2 chloride. Here's copper 2 chloride. So 1 and 3 have the same solute. 2 and 4 have the same solute. That's glucose, a type of sugar. So we're looking at same solute but different concentrations. Capital M, as I mentioned, is molarity, and we read this as 3 molar. Okay, so the unit for molarity, yes, it is moles of solute per liter of solution, and this moles per liter can also be read as a molar. Oh, we have another solution down here, fifth one, and notice what's different here is the volume is a little bit different. All right, so let's look at these and let's answer some questions as we continue through this activity. List the beaker numbers for the solutions in Model 2 that are considered to be concentrated. So we're going to look at the beaker numbers that are considered to be concentrated. All right. Well, it looks like concentrated would be number 3. I guess number 4, maybe this column they're saying here, this column is concentrated. So this column is all concentrated. 3, 4, and 5 are concentrated, whereas 1 and 3 and 2 are dilute. And again, if you just use those words, it's all relative, right? So we want something that is a little more specific. Letter M stands for molarity. And we're going to use the data in Model 2 to answer the questions below. Calculate the ratio of the moles of solute to liters of solution. Here it is. Here's our definition for molarity. Moles of solute to liters of solution for each of the solutions that are above. Moles over liters, moles over liters, moles over liters. It is moles of the solute. And notice it's liters of the entire solution, not just liters of the water, liters of the entire solution. So we're going to calculate these ratios for each solution. I'm going to write it up here just because this is where the numbers are, okay? So let's look at, we are given how many moles and the liters here. These 3 dots are just telling us, showing us kind of a sampling here, okay? It's not necessarily telling us that we have 3 moles. It's just showing a sampling if you were to zoom in there. So here we have 0.06 moles for every 0.06 liters of solution, and that gives us a molarity. 0.06 divided by 0.06 is 1 mole per liter. We don't have a liter, but if we did have a whole liter, we'd have a mole of particles. We only have 6/100ths of a liter, 60 milliliters. Okay? Over here, we've got 18/100ths of a mole, and that is in 6/100ths of a liter, or 60 milliliters. This time we've got, if we take and divide these, you're going to have 3 moles if you had an entire liter. Okay, if you were to have the same concentration but a liter of it, you'd have 3 moles at this same concentration. Here, 0.06 moles divided by 0.06 liters, and you're going to have, if you divide those, you're going to have again 1 mole if you had an entire liter, 1 mole per liter, 1 molar. That's what the capital M is, 1 molar. Here again, 0.18 divided by 0.06 is going to give you the 3 moles per liter, or 3 molar. And here you've got 0.06 moles in only 20 milliliters, which is 2/100ths of a liter. And if you take the 0.06 divided by 0.02, you're going to have your 3 moles per liter, your 3 molar there. Okay? We did all of this, and how does the ratio compare to the molarity of each solution? Well, that's exactly what we just found out. The ratio is moles per liter, and that's what molarity is finding, capital M, also called a molar. All right? Write a mathematical equation to show how the molarity of a solution is calculated. You're going to take moles of the solute, divide by the liters of the solution. You take those two numbers and your answer is going to always be written then in a certain value. The units are moles per liter. The reason why we do this and we write it per liter is so we can compare. Up here, it's hard to compare these concentrations when one of them is 60 milliliters and this one's only 20 milliliters. This one you have 0.18 moles. This one you got 0.06 moles. So we take this, we divide them, we find the ratio, we find out how many moles do you have per liter, moles per liter. This number, now you can compare all the solutions above and find out which one actually is more concentrated. Which type of solution, dilute or concentrated, will have the larger molarity? The more concentrated something is, the larger the molarity, its molarity value will be. Consider beakers 3 through 5 in Model 2. Circle the answer below for the quantity that is the same in all of the beakers that contain 3 molar. So we're going to look at beakers 3 through 5, and we're looking at the 3 molar solutions, and we're trying to circle the answer below for the quantity that is the same in all of the beakers that contain 3 molar. So we're going to look here, is the number of moles the same, is the volume the same, or is the ratio the same? Well, you probably already see what we're going to say here, right? So, is the volume the same for all of them? Well, it is for the first two, but not for the third one. That's 0.02. Is the number of moles the same? 0.18, 0.18, nope, 0.06. But what is the same for all of these, since these are all 3 molar solutions, is the ratio. Okay? We calculate the ratio for all of these, and you end up seeing that, yes, even though the volumes are different, or if the volume is different, then the number of moles has to be different, but it's the ratio that is the same for all of these. So all of these have the same molarity value, are of the same concentration. Okay? It is the ratio that is the same. Explain how beaker 5 with fewer moles can have the same molarity as beaker 4 because it has a smaller volume. So here's the thing with ratios. If you have a ratio, this is your numerator, right? This is your denominator, right? So if your numerator decreases, then your denominator has to decrease as well in order to keep that ratio constant. So if this is equal to a certain concentration, 3 molar, and if this numerator goes down, then the denominator has to go down to keep it the same. And that's what you see here. You can have fewer moles as long as you have an appropriately less amount of, or proportionally a less amount of water. So notice here we've got 0.18 moles. Down here we only have a third of that, 0.06. Well, that's okay, because here our volume is 0.06. Here our volume is a third of that. So everything got decreased by a factor of 3, therefore the ratio is going to be the same. It's still going to be 3 molar. Alright. Can molarity be determined by knowing either the number of moles alone or the volume of the solution alone? No, you cannot find molarity just by knowing the either the moles or the solution. You have to know both. By definition, molarity is moles of the solute. Okay? Make sure it's the moles of the solute, not the moles of the solvent, over the liters of the solution, the entire solution. calculate the molarity of a solution containing this many moles, and there's your solute, in half a liter of solution. All you do is you take 1.5 moles, divide by 0.50 liters, and that is going to actually give you 3 moles per liter, or 3 molar. If you've got 0.4 moles of acetic acid in a quarter of a liter, well, you're going to do the same thing. 0.40 moles, and you're dividing by a quarter of a liter. Moles per liter are always your units here. And 0.4 divided by 0.25 is going to be 1.6 moles per liter, or 1.6 molar. Okay? All right, key point here. Key point here, number 16, we are looking at a 0.5 molar. This time they're giving you the molarity. Did you notice that? They're giving you the molarity here, and now they're giving you the mass of potassium chloride, and then they're also giving you here the volume of the solution. Lots of numbers there. We're going to have to figure out what those values are going to be used for. So let me just pause for a second. Not a bad idea to read the problem again if you're not quite understanding what this is all about. This is your molarity right here. They're giving you the molarity. All right? This here, potassium chloride, this is your solute. This is going to be dissolved in water, but it's not given to you in moles. Look what it's given to you in. Mass. And then what do they give us in parentheses? Oh, interesting. They're giving us the molar mass of potassium chloride, because we can't use mass when we're calculating molarity. We need moles. So we're going to use the mass and the molar mass to convert to moles. And over here we have a volume of the solution, but that is milliliters. So we want liters. So always be aware of units and be aware of all of the values that are given to you, because it can be a little confusing if you don't pay attention. Okay, does the ratio of 74.55 grams over 2,000 milliliters provide the correct molarity? Absolutely not. This is grams. This is not a liter, or that's not liters. That's not a measurement of liters. This is grams per milliliter. If you were to divide these two numbers, your units would be grams per milliliter. That is not molarity. Molarity is always measured in moles per liter of solution. Okay? What units do the amount of solute and the volume of the solution need to be in order to obtain this given molarity? Well, you have to convert the 74.55 grams of the KCl, that's potassium chloride, to moles. Here is your molar mass. They give it to you. You could get this from the periodic table, by the way. All right, you could look that up. You could add up the molar mass for potassium and chlorine, and then find out that they add up to 74.55. I am going to convert this to number of moles. I hope you see how easy this is. I really don't have to do this computation. If our molar mass is 74.55 grams per mole, and you've got exactly 74.55, you've got 1 mole. Okay, but I'm going to show it to you here. That's the molar mass ratio right there, 1 mole per 74.55 grams. So we've got 1 mole of potassium chloride. 200 milliliters. 200 milliliters. Well, there are 1,000 milliliters per liter. So I'm going to divide by 1,000. 2,000 milliliters is 2 liters. Now I can do my calculation. I have 1 mole per 2 liters, which would be the same as, if I take 1 divided by 2, half a mole per 1 liter. So that's how we get the half molar here. Half molar of potassium chloride. Calculate the molarity of a solution containing 2.5 grams of copper 2 chloride in 1 liter of solution. Show your work including units. All right, so I'm going to just set this up. You're going to do the calculation though. All right, we have to convert this to moles. You can't just use grams. You can't use mass for this copper 2 chloride. Okay. So we have to take this 2.5 grams and we need to change this to moles. We have to divide by the molar mass. So you look on the periodic table, find copper, find its molar mass, it's just a number right under the symbol, and then add that to 2 times the molar mass for chlorine, add those numbers up, you should get 134.4 grams for each mole for copper 2 chloride. That tells me I got to take 2.5 and divide by 134.4, and that's going to tell me I have 0.019 moles of the copper 2 chloride. And that is in 1 liter of solution. Well, that was nice. They gave me 1 liter at least. So now to find my molarity, I'm just going to take my number of moles, divide by the number of liters, which is 1, so it's just going to be the same value. That is your molarity. Okay? Number 18, we have, again, a beaker of solution, and it says that it is 3 molar. So there are 3 moles per liter. We don't have a liter, but that's the concentration, 3 molar. Oh, sorry, they're referring to Model 2 up there. What would a 3 molar HCl picture look like if the beaker contained 100 milliliters? If the circle below, in the circle below, visually show the number of solid particles that would be present in any very small volume of the overall solution. Okay, so what they're saying is, hey, can you put in the correct number of dots here? All right. Let's look back up at Model 2 and look at the 3 molar solutions. Let's see how many dots did the 3 molar solutions have. Okay, and then we're going to look at, okay, what if you had a 3 molar solution of HCl? How many dots would that have? If the beaker contained only 100 milliliters. So if you go back up here to our model, look at all these 3 molar solutions. They have 1, 2, 3, 4, 5, 6, 7, 8, 9 dots. 9 dots, 9 dots, okay, because the concentration is the same for all of them. All of these are 3 molar. All right, these are all 3 molar. So if we had another 3 molar solution, we would have 3 dots in our small sample to show that it's the same concentration. All right. Basically what they're saying is it doesn't matter your volume, you're going to show with the concentration is the same. If it's 3 molar, you're going to show the same number of dots in there. Okay? So we would put in our, there's 4, 5, 6, 7, 8, there's your 9. There's your 9 dots. Their point is it doesn't matter the volume of your sample. If the concentration is the same, you would have the same molarity, the same number of particles per liter. Okay? Hey, our lovely extension questions. We love extension questions. Number 19 says a student thinks that she can determine the concentration of a solution based on the darkness or the color intensity of the solution alone. Well, determine the concentration. Okay, you could say it's concentrated or not concentrated or weak or strong. Based on the pictures in Model 2, describe why the student's method will not always work. Well, if you look back up at the model, if you have something that is concentrated, but you just have a small amount of it, it may cause a little bit of a different color. Also, copper chloride here causes a bluish, kind of a blue color for the solution. That's going to make it appear darker here. Whereas sugar, when you put sugar in there, it dissolves clear. In fact, you probably wouldn't be able to tell the difference between a 1 molar sugar solution and a 3 molar sugar solution. So it really depends also on the nature of whatever you're dissolving and the color that it makes and the volume of all of them. So just to say that, hey, it's dark, therefore it must be concentrated, it could be very misleading. Okay, I'm sure you've put something into water that has a strong color to it, and it looks very rich, and then you realize, no, it's pretty weak. Okay, so color alone is not going to tell you too much about the concentration. It could be misleading. Calculate the molarity of potassium chloride if 37.3 grams of potassium chloride are dissolved in water to give a final solution volume of 500 milliliters. Okay, we have to get moles per liter. This is not moles, it's grams. This is not liters, this is milliliters. So this is what I'm going to do. I'm going to write it as 37.3 grams per 500 milliliters. And then I'm going to do a series of multipliers, unit multipliers here, in order to change the grams to moles and the liters to the milliliters to liters. I want to get down here and have a number so that I have moles per liter. Okay? So I'm going to change the grams of potassium chloride to moles. How do I do that? I have to take the molar mass, 1 mole of potassium chloride is going to have a molar mass, I believe, 74, oh yeah, remember it was from up above? Here it is, 74.55, yep. So we can use that exact number, 74.55 grams of potassium chloride per mole. And I know I'm going to put grams in the denominator because I want that to cancel. So now if I take 37.3 and divide by 74.55, I will have the number of moles. It's going to be a fraction. Okay? Excuse me. It's going to be about a half, right? Then I need to convert milliliters to liters. And there are 1,000 milliliters in 1 liter. How do I know that I put the milliliters on top? Because here milliliters are in the denominator and I want those to cancel. So look what happened here. Grams canceled, milliliters canceled by using these two unit multipliers, and I'm going to end up with moles per liter when I do this calculation. If I take 37.3 and I divide by 500 times 74.55, that's going to give me my answer in moles per liter. You can do that. I'll write it down for you. It is a half, okay? A half a mole is what you get up here, and then you're going to have a half a liter, okay, if you did it that way. But if you did this whole calculation, you're going to find out that this is equal to oh, sorry, I forgot the 1,000 up here. My apologies. I was thinking that's not going to give me the answer. I forgot the 1,000. This is going to give me my answer of 1 molar. It's a half a mole. This is a half a mole. This is a half a liter. If you do this whole calculation, you're going to get a half over a half, and you're going to end up with 1 molar, 1 mole per liter. Okay? A student correctly determines that 17.1 grams of sucrose are needed to make 50 milliliters of a 1 molar solution. When making the solution in the lab, the student measured 50 milliliters of water and massed 17.1 grams of sucrose. The student then mixed the two together into a new beaker. The student's resulting solution was not 1 molar. After the student mixed sucrose and water, the resulting solution was poured into a graduated cylinder and it read 62 milliliters. Interesting. Well, what part of the molarity equation did the student overlook when mixing the solution? Let's go back up and look at his procedure a little bit. He determines that 17.1 grams of sucrose are needed to make 50 milliliters of a 1 molar solution. So what he decides to do is he takes and he measures 50 milliliters of water and he takes his 17.1 grams of sugar. He mixes them together. But he doesn't get the 1 molar concentration that he was expecting. Here's why. What you need to do when you're making a solution is you need to keep in mind that the end solution volume has to be a specific amount. If you take a container, all right, and you measure your 50 milliliters, you've measured your water here, all right, and then you put in your 17.1 grams, guess what's going to happen to your volume of the water? It's going to go up. You added something, now your volume of water went up. Now you've got actually your solution is greater than it should be. So he was saying, I want to make a 50 milliliter solution. Well, if you want to make a 50 milliliter solution, you don't put in 50 milliliters exactly of water, because then when you add the solute, it's going to go up. The volume's going to go up. What you must do is this. Here are the steps that you must do. You have to take your container. You have to put in water, and you put in enough water, not up to the mark that you know it needs to be. You don't put it up to, in this case, 50 milliliters. You put it below that. Then you add your solute. You stir that around, get it all dissolved. Then you're going to add more water until you bring the whole solution up to the level where you want it, up to the level where you want your entire solution, the volume of the solution at the end. So what he needed to do is he needed to add water way below the 50 milliliter mark. If he wants 50 milliliters to be his final volume of his solution, add water below that, then add your solute, stir it all up, get everything dissolved of the 17.1 grams. Then once it's all dissolved, add more water to bring it up to the 50. Now you've got 17.1 in your 50 milliliters. Okay? Don't get confused. This 17.1 would not give you, this is grams. Okay? So somehow you converted that to moles to find out how many moles he had. But the point is, you have to add the solute to a lesser amount of water, dissolve all of it, then once it's all dissolved, bring the water level or the solution level up to the point that you want it in order to get your correct measurement, okay, to get the volume that you are desiring. Okay, I hope that's helpful, and this pretty much is kind of wrapping up our section here on solutions. We've been spending a lot of time talking about saturated and unsaturated, solubility, non-molarity, concentrations. So I hope this has been helpful, and we will see you in the next video.